Hi guys, this is Raina and Abhishek, and today through the video lecture, we're going to explain to you the Michelson Morley Experiment. The Michelson Morley Experiment was a scientific experiment to find the presence and properties of a substance called ether, a substance believed to fill empty space. The experiment was done by Albert Michelson and Edward Morley in 1887.
Since waves in water need something to move in, and sound waves do as well, it was believed that light also needed something to move in. Scientists in the 18th century named this substance ether, after the Greek goddess of light. They believed that ether was all around us and that it also filled the vacuum of space. Michelson and Morley created this experiment to try and prove the theory that ether existed. They did this with a device called the interferometer.
The basis of this experiment was that many early scientists believed ether to be fixed with respect to the sun. But if this was any true, the speed of Earth around the sun would bring about a change in the speed of light. So, the experiment was conducted in fact to test if ether was an absolute frame of reference or not. So how this thing works is, using a beam splitter, a light source is split into two arms. Each of these is reflected back towards the beam splitter, which then combines their amplitudes interferometrically. The resulting interference pattern is not directed back towards the source, is typically directed to some type of photoelectric detector or camera. Depending on the interferometer's particular application, the two paths may be different lengths or include optical materials or components under test.
Okay, so in this slide, we see the phase shift between light traveling the longitudinal versus the transverse arms of the Michelson-Morley apparatus.
And now we're going to show you what the calculations of this experiment look like.
Here are the calculations for the experiment.
Light path analysis and consequences. The beam travel time in the longitudinal direction can be derived as follows. Light is sent from the source and propagates with the speed of light c in the ether. It passes through the half-silvered mirror at the origin at t equal to 0. The reflecting mirror at the moment is at a distance of L and is moving with a velocity v. The beam hits the mirror at time t1 and thus travels a distance ct1. Consequently, the travel time t1 is L upon c minus v. The same consideration applies for the backward journey with the sign of v reversed. So the total travel time t longitudinal is L upon c minus v plus L upon c plus v, which is time t1 and time t2, which eventually results in 2L by c into 1 upon 1 minus v square by c square. After applying binomial approximations, we get the final result as 2L by c into 1 plus v square by 2 c square. Michelson obtained this expression correctly in 1881. However, in the transverse direction, he obtained the incorrect expression. T transverse is equal to 2L by c. This is wrong. Now let's look at the reasons why. This is wrong because he overlooked the fact that ether wind also affects the transverse beam time. But fortunately, this is corrected by Alfred Potier. The beam is propagating with the speed of light c and hits the mirror at time t3 traveling a distance ct3. Mirror meanwhile has travelled a distance vt3. So the actual travel beam distance is root over of L square plus vt3 whole square. Thus ct3 comes out to be root over of L square plus vt3 whole square. So the final t3 calculations are as follows. Then we finally calculate the time difference between time longitudinal and time transversal, and this time before rotation is given by this, and after rotation of the Earth, is given by this expression. This is referred to as del 1 and this is del 2. So now we finally divide the difference in the two by the wavelength lambda, and the fringe shift n is found to be del 1 minus del 2 upon lambda, which approximates to 2L v square upon lambda c square. Since L is equal to 11 meters and lambda equal to 500 nanometers, the expected fringe shift was n equal to 0.44. So the result would be a delay in one of the light beams that could be detected when the beams were recombined through interference. However, this negative result led Michelson to the conclusion that there is no measurable ether drift.